and integrals of inverse trig functions. And so we need to clearly define what inverse trig functions are before finding derivatives and doing the calculus side of it. So we've got a graph here of f of x equals sine of x. We want to define the inverse of sine as a function, and so we want a one-to-one relationship here. So basically we're looking to take a chunk of the sine graph that has all of the values between -1 and 1 included, and included only once. And preferably we would like to have it centered around 0, close to 0, so that we're not making it unnecessarily complex. We could choose any section of graph and make this work, but just to kind of have consistency's sake, we are going to take the values here from -π/2 to π/2. So that is a range of values there that gets us y values between -1 and 1. So when we look at inverse sine, our inverse sine is going to have a domain of -1 to 1 that matches up with the range on the red sine graph here. Okay, and then the range of the blue graph, the y values it can take on, are going to match up with the domain that we restricted here for f of x. So we're going to go here from this point, which is at -1, -π/2, all the way up to this top point, which is at 1 π/2. All right, so it's important when we're talking about inverse trig to understand the restrictions, the domain and range of each individual function. So that's how it works with sine. If we look at cosine, okay, we wouldn't want to take the same kind of values here, because if we went from -π/2 to π/2 again, we would have y values that repeat, and we also would be missing out on the negative section of the graph. So with cosine, instead of going from -π/2 to π/2, we're going to restrict the domain here to make it from 0 to pi. The y values are still going to go between -1 and 1. So if we now go and look at inverse cosine, see a graph that is completely above the axis here, because if we are going to have all positive values in the domain of cosine of x, the range of inverse cosine is going to be all positive. So again, we can kind of scroll on the graph here and see that it goes from -1 pi all the way over here to 1, 0. So again, the domain is going to be -1 to 1, and the range is going to be from 0 to pi. So that's how the graphs of inverse cosine and inverse tangent look. And we're going to take a look at how to get the derivative formulas, how to derive them, where they come from, and then how to use them. And then also a little bit about how to work backwards and do some integration. So let's take a look at how we would find the derivative of inverse sine, knowing that the domain is from -1 to 1, and the range is from -π/2 to π/2. So we're going to start out with saying if y is the inverse sine of x, then x must equal sine of y. This is just definition of what an inverse is about. We're going to use implicit differentiation on each side. So we're going to take the derivative of each side with respect to x. The derivative on the left side is just 1. On the right side, the derivative of sine is cosine. And then we need to have the y prime on here, because in order to take the derivative with respect to x, we're going to take the derivative with respect to y and multiply it by the dy over dx, or the y prime. Going to divide each side by cosine of y. And so you end up with y prime is equal to 1 over the cosine of y. Now, we would like to have the derivative in terms of x, because that's how the original function was written. So we're going to go over here to the side and just think about this. We've got sine squared y plus cosine squared y is equal to 1, the old Pythagorean identity. So we know cosine squared is equal to 1 minus sine squared y. we could take square root of each side and say that the cosine of y is equal to plus or minus the square root of 1 minus sine squared of y. Now, we know here that the cosine of y must be greater than 0 because our y values are between negative pi over 2 and pi over 2. That's part of our restrictions on here with inverse sine. So if cosine has to be positive, then we know that the cosine of y is going to equal positive square root of 1 minus sine squared of y. Now here's why that helps us out. Way back up here, we said that x is equal to sine of y. So if x is equal to sine of y, then this sine squared can be rewritten as 1 minus x squared. So this is our cosine of y. I'm going to take that, and now I'm going to go back into the original problem. So a little dotted arrow going back in the other direction now, after we've done that side work. And cosine of y is equal to the square root of 1 minus x squared. And so that is our y prime. So this is telling us that overall, the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. And this is going to apply for x that are between negative 1 and 1. But this is true because of the domain of inverse sine. This isn't anything special that you would need to know there. It's just where it's useful. You can do a similar proof and find that the derivative of inverse cosine is equal to negative 1 over the square root of 1 minus x squared. Now that we've got derivatives for inverse sine and inverse cosine, let's take a quick look at how we would get inverse tangent's derivative. Same concept to start, that if x is equal to the inverse tangent, if y is equal to the inverse tangent of x, then I'm allowed to say that x is equal to the tangent of y just by how we define inverses. Okay, so again, taking the derivative of each side with respect to x, I'm going to have 1 over here. Derivative of tangent is secant squared times the y prime. Same idea, I'm going to divide each side by secant squared. Okay, and I'm going to use a trig identity again. The trig identity that is useful to us in this situation is that the secant squared of y is equal to 1 plus tangent squared of y. Now, sometimes people have a hard time remembering the relationship there between secant and tangent. If you take the Pythagorean identity, sine squared plus cosine squared is equal to 1, and you think about what would happen if you take each of these and divide them by cosine squared, it makes the identity a little clearer that you have tangent squared here plus 1 equals secant squared of y. So that's where that identity comes from. If you forget it, that's a good way to get it. You can also divide each of those by sine squared and get a relationship between cosecant and cotangent. Now that I know that this is true here, I can plug this 1 plus tangent squared in for secant squared. And since the tangent of y is equal to x, I can make the substitution that tangent squared of y is just x squared. So this is our y prime, and it tells us that the derivative with respect to x of inverse tangent is equal to 1 over 1 plus x squared. And if we go in reverse, that actually gets us a useful integral that is going to come up quite a bit. That we can also say then that the integral of 1 over 1 plus x squared is equal to inverse tangent plus c. Okay. And similarly with the inverse sine and cosine, if I take the integral of 1 over square root of 1 minus x squared, that's going to be inverse sine. And finally, if I take the integral of negative 1 over the square root of 1 minus x squared, that's going to give me inverse cosine. Don't forget the plus c.